So the last numerical that we did was based on equilibrium of a point charge. There's one more numerical in previous year's question, which is based on, instead of equilibrium of a point charge, that's equilibrium of a system. So if I'm saying a system of 3 charges is in equilibrium, system is in equilibrium means net force on each of the individual charges is zero. I'm repeating it again. If I'm saying a particular charge is in equilibrium, that means the net force on that particular charge is zero. If I'm saying a system is in equilibrium, that would mean the net force on each of the individual charge would be zero. So let's start with this question. First, write this statement. If a system of charges is in equilibrium, then net force on each charge is zero. If I'm saying that a system is in equilibrium means net force on each of the individual charges is zero. So the question is, two charges plus E and plus 4E are placed at separation A. A third charge Q is placed on the line joining the two charges Calculate so that system is in equilibrium. So that the system of charges is in equilibrium. Calculate first position of charge. Calculate position of charge. Second, nature of charge. Nature and magnitude of the charge. Nature and magnitude of charge. So yesterday the numerical we did, in that numerical we have calculated only position of charge. But now you're supposed to calculate both nature as well as magnitude of charge. Let's solve it. So if a charge is in equilibrium, that means just have to check the net force over that particular charge should be zero. But when we are saying that system is in equilibrium, that would mean the net force on each of the individual charge would be zero. If you're saying that system is in equilibrium, that would mean that net force on each of the individual charge would be zero. So let's say you have a charge plus E and a charge plus E, 4E. This is plus E. This is plus 4E. They are placed at a separation A. Let's say this point is A, this point is B. In between them, I place a charge Q, a positive charge Q. Now you have to decide for this charge Q, can this system be in equilibrium? System be in equilibrium means net force on each of the individual charges zero. So say we are trying to calculate the net force over this charge Q. So what are the net forces on charge Q? So this Q will experience a force by this charge at A. Fatma, what should be the direction of force on Q by A? That's my right hand, this one is left. Direction of force on charge Q by charge at A.
Right side.
Right side. And the name of the force? It's FOA, right?
Oh yeah.
We're calculating the force on O due to A, then that would be FOA. In the same way, what's the direction of force on O by charge at D? This charge at D will repel this thing, huh? What should be the direction of force?
Left side.
Left side. The name is
FOB.
Similarly, the direction of force on charge at A. So Froza, what's the direction of force on charge at A due to charge at O? The name of force, Froza? Force on A by charge at O. Yes, FA. Good. What about the direction on force on charge at A due to charge at D? left, right. And the name of the force is FA. Now see, these two forces are acting in opposite directions. So this charge Q could be in equilibrium. Two forces which are acting in opposite directions can cancel each other. But here, this FAO and FAB, they're acting exactly in same directions. So forces which are acting exactly in same direction, they just can't cancel each other. So for this, for plus Q, charge E cannot be in equilibrium. So Fatma, is the system in equilibrium? Can you say that the system is in equilibrium?
No.
No, system would be in equilibrium if net force on each of the individual charges is zero. But in this particular case, the net force on charge at A is not zero, so it can't be in equilibrium. So let's check the equilibrium by just changing the nature of Q. Instead of plus Q, let's take a minus Q, and this is B, and this charge is plus OA. Just like before. So this charge at A will attract this charge at O. It's a negative charge now. So this would be the direction of force. This is force on charge at O due to charge at A. Similarly, the charge at B will attract this charge. The direction of force is FOB. So both the forces are acting in opposite directions. So this minus Q could be in equilibrium. Just like minus Q, if we talk about this A. This charge at O will attract this charge at A. This is the direction of force. Force on charge at A due to charge at A. Similarly, the charge at B will repel this charge at A, and the direction of force will be left hand side. This is force on A by B. Again, both the forces are acting in same direction, so charges could be in equilibrium. In the same way, over this B, this charge at O will attract this charge at B. The direction of force is FBO. Similarly, charge at A will repel this charge at B, and this would be the direction of force FBA. Again here, FAB and FAO, they're acting in opposite directions, so they can easily cancel out each other. This FBO and FBA, they're again acting in opposite directions, they can cancel out each other. So forces which are acting in opposite directions can cancel out each other. So in this case, for minus Q, your system could be in equilibrium. So this part of the question, nature of charge. So you got the nature. The nature of charge is negative. Your charge Q should be a negative charge. Just note it down, and then you start the complete calculation. So this is important. The system cannot be in equilibrium for this plus Q, but the system would be in equilibrium if charge is negative. Fatma, for position of charge, we have to calculate. For position, we will take equilibrium of this charge minus Q. So this is charge plus E. This is 4E. Now this is minus Q. This charge can't be positive. This is A, this is O, this is B. The separation between this E and 4E is A. Let's say that, let's call this particular separation as X. This as X. So this will be A minus. This will remain A minus. So that force on O is charge at A will attract this charge at O, and the direction of force is this FOA. Similarly, charge at B will attract this charge at O, and this is the force. Both the forces are acting in opposite directions, so they can easily cancel out each other. We're supposed to calculate this X. So for equilibrium of minus Q, net force should be 0. Net force should be 0. So you can simply write this as it's FOB plus FOA is 0. Now since FOB and FOA are acting in opposite directions, you can subtract them. So this is FOB minus FOA is 0, or you can write this as FOB is equal to FOA. Now FOB and FOA are acting in opposite directions, so you can write this as this is K FOB, force on charge at O due to charge at B. It could be K Q 4E over the separation between them, which is A minus X square. See, I'm not taking negative sign here. The negative sign will decide the direction of force. We won't consider negative sign while calculating magnitude. In the same way, FOA. So FOA is simply it's K. At O the charge is Q. At A your charge is E divided by its X square. So you can calculate this K with this K. You can cancel this Q with this Q. This E will cancel this E. So you are left with 4 by A minus X whole square is 1 over X square. In the next step, you can take roots on both the sides. So it would be 2 by A minus X is 1 over X. Just cross multiply them. You will get 2x is A minus X. Or this is 2x plus X would be A. So you can simply write 3x is A and your X would be A by 3. X is A by 3, simply A by 3. Now, that's the first part of the question. To calculate charge Q, the value of charge Q, you can take equilibrium of any of the charge. You can take equilibrium of A or equilibrium of B. The forces acting on A are charge at O is attracting this charge at A, so that's FAO. B is repelling this charge, so that is FAB. Now again, if I'm taking equilibrium of plus E. The net force on plus E is 0. That means FAO plus FAB is 0. So here, FAO and FAB are acting in opposite directions. You can subtract them. This would be FAO minus FAB is equal to 0. Or you can simply write this FAO is FAB. Fatma, what's the magnitude of FAO? Magnitude of FAO, Fatma.
KQ
Yeah.
E by A minus X square.
By X square. Good. What about FAB?
For K
Yeah.
for
KE.
KQ for E.
Not Q. You are calculating.
KQ for E.
Not Q. Not Q, Fatma. You are calculating force on A by due to B. So there is no Q here.
Okay.
So again, let's just tell me the magnitude. K, then
4E
4E. Okay.
by A minus X square.
What is the next charge? What's the second charge?
E.
E. And what about the separation between E and 4E?
A.
A square, right? So this E will cancel this K. This E will cancel this E. So your Q is, it's 4E X square over A. Say this is equation number 1 and this is equation number 2. You can easily substitute the value of X from 1. Just on substituting 1 in 2, you will get that Q is, it's 4E over A square into X square. So X is A square by 9. So this A square will cancel this A square. And you will get that your Q is, it's 4E over 9. Now, the charge is negative, right? This Q is a negative charge, so put a negative sign over it. So for a system to be in equilibrium, you have to place this charge minus Q having magnitude 4E by 9 at a separation A by 3 from E. If these are the values of charges in position, then entire system will remain in equilibrium. So that was the last question on Coulomb's law. The next is electric field. See, electric field is the space around the charge, and in that space, the electrical properties of charge exist. Say if you have a charge Q, then there must be a space, a region around that charge. Within this region, the electrical properties of this charge plus Q exist. Electrical properties exist means if you bring another charge, let's say if you are taking a charge Q over here, then this capital Q can attract or repel this small q. But if you place this small q outside the field of capital Q, then capital Q cannot attract or repel this charge Q. So electric field is simply the sphere of influence, or you can say the region of influence. Electric field is the region around the charge, and within that region, the electrical effect of this charge exists. Once you move outside that particular region, the region known as electric field, the electrical properties of charges will vanish. This capital Q cannot exert electric force over another charge if that charge is placed outside the field. So electric field, it can be defined as electric field is the space around the charge, in which its electric properties exist. So electric field is simply the space around a charge, and within that space, electrical properties of charges exist. That's electric field. Now, if I take electric force, the Coulomb force, so what you think, that electric force is property of one charge? Or for electric force, you should have at least two charges? So what you two think? For electric force, you need at least two charges. Like say, if you have a charge Q1, only Q1, it can't experience any force. It can experience any force only if there is one more charge. Yeah. So electric force is property of at least two charges. While field is the property of a single charge. Even if you have a single charge, that charge will generate field around itself. Even if you have a single charge Q, then that charge Q will generate an electric field around itself. So electric field is the property of single charge, or So even if you have a single charge, that single charge will generate its electric field. But the issue is, since field is not visible, say if I take this pen and somehow I have charged this pen will generate an electric field around itself, but that field is not visible. Just by naked eye or just by any electron microscope or anything, I can't see that field. That field is not visible. Now to detect whether field exists at a particular point or not, you have to use another charge. I'm repeating it again. Whenever you have a charge, let's say this pen is charged, this pen will generate a field around itself, but that field is not visible. So to detect whether field exists at a particular point or not, we use another charge. Say this is charge capital Q. I just want to detect whether field exists over this point or not. So to detect field, I place another charge Q, test charge Q over this point. To detect whether field exists or not over this point, I place another charge small q over this point. If capital Q could exert a force over this charge, if Q experience a force, that means this Q is within the field of capital Q. If this Q doesn't experience any force, that means this Q is outside the field of capital Q. So test charge will experience a force only if it is within the field. This will experience force only if it is within the field. So just to detect whether field exists or not, we will bring a charge, which is known as test charge. If test charge experience force, that means field of capital Q exists over this. Does the field have a Fatima? No, it doesn't have any shape. Field doesn't have any shape. Field is just like, you can consider it as a fluid. Once you bring a charge, then around the charge, in the space around the charge, you can consider some sort of fluid, like, or better than fluid, you can assume some sort of radiation, that field. Light is basically a combination of electric fields. You can consider your field as sort of radiation. So whenever you bring a point charge, around that point charge, a sort of radiation develops that you call electric field. And to detect that field is not visible. And to detect that field, you will put a charge over it, a test charge. If test charge experience 4, that means field exists over this point. So is it clear up to this point? To detect field, we use test charge. Now, another interesting thing. Now, the force that this Q experience is no longer directly due to this capital Q. The field that this small q experience is not directly due to this capital Q. It's rather a two-step process. In the first step, this is capital Q. This capital Q will generate an electric field. That's the first step. Next, if you place another charge in this field, E, and the charge Q in this field, then this field will exert force over this test charge. So now force, you can say that this force is a two-step process now. In the first step, a charge generate field, and in the second step, that field exert force over another charge. So the charge which is generating field is capital Q, which is generating field. So we say this capital Q as the source charge. And the one which is experiencing force, we call this as a test charge. So F is force on test charge Q due to electric field of source charge capital Q. So from now onwards, whenever you will think about electric force, consider this as a two-step process. The first step, a charge will generate field, then that field will exert force over another charge. So is it clear up to this point? Because from now onwards, we will deal with field, not with force. So field is simply the space around the charge. Next, once we know field, we know that around the charge, something exists which is electric field, and that electric field is exerting force over another charge. Now the next step is you have to calculate that field. You have to measure that. How we would measure that field. So to measure that field, we use the concept of electric field strength. When we try to measure the magnitude of field, the quantity that we use is electric field strength or intensity. This is also known as electric flux density. Electric flux density. In CRT have used all these three names for electric field strength. electric field strength. So electric field strength simply means when you try to measure the value of electric field, the quantity that you came across is electric field strength. So you have a charge capital Q. At a separation R from this charge, or this is point P. You're supposed to calculate the value of field at point P due to capital Q. So capital Q must be generating a field over this point. We represent field with E. This E represents the strength of field that we want to measure. To measure this field P, what we do, we put a test charge Q over this point. Just to measure the value of field at point P, we first put a test charge over this point. We put a test charge Q over this point. This test charge Q experience a force. That force is F electric. It experiences a force which is F electric over this point. So electric field at P is the ratio of electric force experienced by the test charge. So let's write some detail of it. Electric field at P, or electric field of source charge capital Q at point E, P. So that's your source charge. So over this point P, the field of source charge is simply the ratio of force experienced by the test charge. This is the F is the force which is experienced by the test charge, divided by the magnitude of S. The ratio of the force and the charge is field. This is the definition of field. This is how we calculate field. So what is F? F is the force on test charge Q by source charge capital. This is the force on test charge small q due to source charge capital Q. Now to calculate this field, you just calculate the force over the test charge and just take the ratio of force with the test charge. Okay. There's one more issue. Okay, Afroza, just tell me, can this capital Q source charge experience a force? Is it possible that this capital Q will experience a force?
Yes.
Okay. Exert capital Q. If you're saying that capital Q experience force, who will exert force on capital Q?
The test charge.
Test charge. So due to that force, this capital Q can displace. If this cap, then it can displace, right?
Yes.
Okay. This will it force F, the force under test charge? Yes or no? Capital Q gets displaced. Effect,
Yeah, it should, I guess.
it will change. If force changes, because force is related to field, if force changes, then field should change.
Yes.
So to calculate the fixed value of E, this F should be fixed. And to fix this F, this capital Q should be fixed. And to fix this capital Q, we can do two things. There are two methods to fix this capital Q. The first method is you can just fix this capital Q by some unidentified forces. Like you can just bound this capital Q with a thread or a wire, or you can just stick it with a glue to the surface, this capital Q to the surface, so that this capital Q does not move. That's the first method, but that method is non-mathematical. Another method is, since you have already said that this capital Q will move due to small q, if I take this small q as very small, if you consider the value of small q is very, very small value, then in that case, if this small q is a very small charge, then it can't practically repel this capital Q. It's a very, very small charge, like 0.000001 coulomb charge. So if the small q is a very, very small charge, then the small q cannot practically repel this capital Q. That you can write this, its limit q tends to 0. When I'm saying that q tends to 0, that simply means q is an extremely small charge, a very, very small charge. So this is how we calculate electric field. This is the magnitude of electric field. This limit q tends to 0 is, we are using this limit just to ensure that this capital Q doesn't move. Because once this capital Q moves, then force F will change. Once your F changes, your electric field changes. So to measure this electric field, you need to put this capital Q at rest. That you can do by two methods. Either you can fix this capital Q by some unidentified force. You can just fix it using a rope or a thread, or you can stick it using a glue. But these methods are non-mathematical. Theoretically, mathematically, we can fix this Q, capital Q, just by taking the value small q is very, very small. If we take this small q, very small, limit q tends to 0, then E is limit q tends to 0 as well. Now, this is how we calculate electric field. It's force experienced by charge divided by magnitude of test charge. The next thing. The next is, if I put Q equal to 1 coulomb, then your electric field will be exactly equal to force. So this is the statement from which we can write the definition of electric field strength. So you can say that electric field strength at a point is force experienced by unit positive test charge placed at that point. So at a point, electric field strength is force experienced by unit positive test charge. Unit positive test charge means charge of 1 coulomb. So if you place a charge of 1 coulomb over this point, whatever the force this charge experiences will be equal to electric field of source charge. Okay, so if this magnitude is clear, the next is the direction of field. See, the direction of field is direction of electric field is same as that of force experienced by positive test charge. So the direction in which the positive test charge will experience force is same as that of direction of electric field. Say you have a source charge here, capital Q, and this is your test charge. You just want to get the direction of field of this capital Q over this point. So this capital Q will repel this test charge Q in this direction. This is the direction of force, and this would be the direction of field. Force is experienced by test charge, and field is of source charge. Fatma, this is minus Q and this is test charge. Can you tell me the direction of force? Force will act in the right hand side or to the left hand side?
Left hand side.
So this Q will move to the left hand side. This is direction of force. Then what should be the direction of field, Fatma? The direction of field will be exactly same as that of force. So direction in which this test charge is experiencing force is same as that of force. So direction of field and direction of force is also same. Both will act in same direction. So till now, whatever we have done for electric field is very generic. Like all these results are valid for any type of charge configuration. Your charge could be a point charge, it could be a sphere, it could be a rod, it could be anything. But now we will derive some relations which are precisely valid for a point charge. We will derive some relations which are valid only for point charges. So first we will calculate electric field. So you have a charge Q, source charge. Now this source charge is a point charge. This is source charge. This is source charge, which is a point now. At a separation, say some separation R from the source charge. At a separation R from the source charge, I want to calculate field. I want to calculate field over this point due to source charge. Let's call this point as P. So Fatma, what should be the first step? You're supposed to calculate field at P due to capital Q. What should be the first step, Fatma?
We should calculate the force on P due to Q.
On P due to Q, or you will first place a test charge over the point?
Yeah, first the test charge.
First the test charge. So let's place a test charge Q over this one. Now, Fatma, what should be the direction of force? No, not Fatma, Jubena. Jubena, what should be the direction of force on small q due to capital Q? Direction of force on small q.
It should go away.
It should go away. So the direction of force is to the right or to the left?
To the right.
Right. So this F is the force on test charge Q due to electric field of source charge capital Q. So we want to calculate force on test charge Q due to electric field of source charge capital Q. Okay, can we calculate this force, Afroza? What should be the magnitude of this force since both the charges are point charges? Can you just calculate the magnitude? Afroza, the magnitude of this force. Just Coulomb's law. Yeah. So that's K QQ over X square. It's force now. And not X, it's the separation is R, so it's KQ by R square. And again, it's only magnitude. I'm writing complete force, so just use a unit vector R cap. So I'm using a unit vector R cap in this direction. That's it. Now, electric field E of capital Q. So Fatma, what's the formula to calculate electric field? We just have discussed in the last section.
Force by the magnitude of Q.
Yeah. So that's limit Q tends to 0. It's force F over the magnitude of Q. Let's call this as equation number 1 and say this is equation number 2. Let's substitute 1 in 2. On substituting 1 in 2, this E is its limit Q tends to 0. It's 1 by Q multiplied by F. F is KQQ over R square, then R cap. The small q will simply cancel this capital Q. And we are left with only the value of field is its limit Q tends to 0. This is simply KQ over R square into R cap. Since no small q is left, there is no small q in the entire calculation. So we can just drop this limit now. This limit is over q. This limit simply tells you that small q is very small. That's it. It says that q is in the neighborhood of 0. It's a very small charge. That's it. Now, since we don't have any q in the calculations, we can just drop this limit and we will write it as its kq over R square multiplied by R cap. So this is how we calculate field. Electric field is kq by R square into R cap. Yes, Fatma, electric field is a vector. Yes, it's a vector. That's why we have considered its direction. That direction is same as that of force. So this is it. It's kq by R square into R cap. The next is, if you just want to calculate only magnitude, you wish to calculate only the magnitude, then you can simply drop this R cap. This R cap we are using to specify the direction. If you just drop this R cap, then you are left with only kq by R square. Or it's simply 1 over 4 pi epsilon naught. It's q by R square. Now see, we were calculating the field of capital Q, and the final expression we are getting only capital Q. This is what we have discussed initially, that field is property of a single charge. If you are calculating field of capital Q, then you will get only capital Q. If you are calculating field of small q, then you will get small q. So the field, the magnitude of field depends only over the charge. It will depend only over the charge. It's kq by R square, 1 over 4 pi epsilon naught q by R square. Okay, the next thing is, okay, Fatima, can you just check the direction of force? What should be the direction of field? Can you predict the direction of field from this expression and from this diagram? It will act to the right hand side or to the left hand side, Fatima? Yeah, so the force is acting to the right hand side, right? The field
Oh, yes.
in the same direction. The direction of field is same as that of force experienced by test charge. So field 2 will act in this direction. Padma, right? The direction of field will be same as that of force. So field 2 will act in the same direction. Okay? Now, for the direction of field, you can use one more shortcut trick for direction of field. You can use one more shortcut trick. So direction of field for positive charge, it's away from charge. If you have a positive charge, then direction of field is away from charge. If you have a positive charge, then direction of electric field is away from the charge. Say you have a charge plus q, then the direction of field is away from the charge. This is the direction of field. And for a negative charge, direction of field is towards the charge. You can do it directly. If you remember this thing, that then you won't need the this force to calculate the direction of field. You can predict the direction of field directly. Say this is positive charge. Na? I'm asking you to calculate the direction of field over this point. Direction of field is simply away from the charge. Away from the charge is right. So what, Fatma, what should the direction of field over this point due to plus q? Direction of field over this point due to plus q. Will it be upwards or outwards or downwards?
Downwards.
It's away. Away means in this case it would be downwards. If I need direction of over this point, then again it's away from the charge. Away means Fatma, it would be rightwards or leftwards?
Left.
Left. It's always away. That is the direction.
What if the source charge is negative?
Yeah, that's that we are coming. That's the next. For negative charge, it's towards the charge. If you have a negative charge, then direction of field is towards the charge. So if you have a charge minus q, and this is fine, then field will act towards minus. That's it. So over this point, the direction of field is towards the charge. So if you remember this thing that for a positive charge, direction of field is away from the charge. And if you have a negative charge, then field will act towards the charge. They can predict the direction of field directly. And one more thing. What should be the unit of field, electric field? Open question for all. What is the direction of unit of electric field? SI unit. What is the SI unit of electric field? Yeah, Newton per Coulomb. Electric field is force divided by charge. So electric field is Newton divided by Coulomb. So SI unit is Newton per Coulomb, or there is one more unit of electric field, which is volt per meter. This unit of volt per meter we will discuss in the next chapter. The unit of volt per meter we will discuss in the next chapter. The first question is, plot electric field versus R graph for a point charge. Electric field versus position graph for a point charge. So electric field is for a point charge, electric field is kq by r square. So electric field is inversely proportional to r square. Now once they are inversely proportional, so if you plot E versus R graph, this is R and this is E. This is R and this is E. So if you plot E versus R graph, then the graph would be hyperbolic. They are inversely proportional, so graph would be hyperbolic. If you keep on increasing R, then E will decrease. Right? But can you just guess the shape of the graph if I'm writing E versus 1 by R square? Again, this is for all three. If E versus R graph, the shape is known as hyperbolic. Hyperbolic. Very good, Afroza. Yeah, if right. So E versus R, E is inversely proportional to R square, R, so graph would be hyperbolic. But if you need to plot E versus 1 by R square, then your E is, now, for this variation, put 1 by R square as another variable x. Then you will know that E is inversely proportional to R square, which would mean that E is proportional to x, right? We are considering 1 by R square as a variable. So E is inversely proportional to R, that means it's directly proportional to x. If it is directly proportional, then your graph should be a straight line. It would be a straight line graph if you are plotting E versus 1 by R square. This R is in meter and this E is Newton per Coulomb. This E is Newton per Coulomb. Let's do a formula-based numerical, a simple formula-based numerical, just to know how to use this formula. So charge of minus 2 Coulomb is placed at origin as shown in figure. As shown in figure. Calculate electric field. Calculate electric field at a separation of 3 mm from the charge. So you have a charge minus 2 Coulomb. This is placed, not plus. This charge is placed at the origin. This is origin of the coordinate system, place the charge minus. So this separation is 3 mm. You're supposed to calculate electric field over this point. And I need electric field with proper direction. You have to use unit vectors I cap, j cap, the proper unit vector I cap, j cap, or k cap. Just calculate it and report your answer in chat. The simplest version of electric field, the first numerical. Magnitude of I cap, j cap, k cap is 1. They are unit vectors. Huh? Whenever you have unit vector, this magnitude is always 1. See, you're supposed to calculate the field over this point. Let's say you are supposed to calculate field at point P. No, Fatima, it won't be all. See. So the field, the magnitude of these at this point will be kq over r square. So here q is minus 2 coulomb. But we won't put the magnitude, the nature of charge. We won't put this negative sign in this expression since we are calculating only magnitude. Next, your r is 3 mm. So that simply means 3 into 10 raised to the power minus 3 meter. And k is as ever 9 into 10 raised power 9. So that's 9 into 10 raised power 9. Charge is 2 over r square, which is 3 into 10 raised to the power minus 3 square. So this is 18 into 10 raised to the power 9 by 9 into 10 raised to the power minus 6. So you can just calculate the ratio of 9 and 18. This is 2. See, this is the magnitude, right? So the magnitude is 2 into 10 raised to the power 15. So that's 2 into 10 raised to the power 15. So the direction, what do you think? What should be the direction? It should be along right hand side or the left hand side over this point? Left, good. Good. So Afroza, can you just tell me the unit vector which is acting along this direction to the negative x-axis? What is the unit vector which is acting along negative x-axis? A unit vector acting in this direction. Is it I cap or minus I cap? I cap is along positive x-axis, right? But this is negative x-axis, so the unit vector is minus I cap. Now, to express this result in proper vector form, this is Newton per coulomb. This is just magnitude. To express this in proper vector form, just multiply it with a unit vector minus of I cap Newton per coulomb. Right? If it were up, if the direction is along y-axis, then we would have used j cap. Direction is along negative y-axis, then we will use minus j cap. So you will not get many questions for a single point charge. Majority of questions will include a system of point charges. So whenever you have a system of point charges, we use superposition principle. It's the same principle as we discussed in force. The same principle that we have discussed in force. The only difference is that was for force, this is for the field. So if you have a system, so for a system of n interacting point charges, net electric field or total electric field at a point is vector sum of electric field due to individual charges. Vector sum of electric fields due to individual charges. So if you have a system having n point charges, then electric field at a particular point is vector sum of electric field due to individual charges. So let's say you have a system of n point charges. You have a charge q1, a charge q2, and a charge q1. And you're supposed to calculate field over this point. So over this point, just calculate field due to each of the individual charge. Field due to q1, field due to q2, field due to qn. So we'll first calculate field due to each of the individual charge. That's E1, this is E2, this is En. We'll first calculate field due to each of the individual charge. So if I say this separation is R1, I call this separation is R2, and I say this is Rn. Then the magnitude of individual fields is E1 is K Q1 over R1 square. If you want to take this in a proper vector form, this will be R1 cap. Similarly, you can write your En. En will be KQN over Rn square and a unit vector Rn cap. So the net field is simply the vector sum. Keep on adding them up vectorically. It's simply E1 plus E2 up to En. Keep on adding vectorically. So that's the net field over a point. So if you have a system of more than 1 point charge, then just calculate field due to individual charge and add them up vectorically. In the next numerical, we will use a concept of neutral point. We will use the concept of neutral point. So neutral point simply means point at which net electric field is 0. That's neutral point. So neutral point simply means point at which net electric field is 0. So the point at which net electric field is 0 is known as neutral point. So let's start with this question. So you have two charges. Let's say a charge plus E, and we consider another charge minus 4E. They are placed at a separation A. Or say this is plus 4E. They are placed at a separation A. You are supposed to calculate a point at which point on the line joining the two charges where field is 0. So you're supposed to find the position of a point at which the fields due to these 2 point charges will cancel each other. Now that point may lie in any of the 3 regions. It can lie in region number 1. That point could lie in region number 2, or that point could lie in region number 3. So first of all, you have to find the appropriate region in which net field can be 0. Let's check in the region number 1. So Giovanna, what should be the direction of field due to this charge at A in this region 1? Okay, so it should be right hand side or left hand side?
LHS, I mean left hand side.
Should be left hand side. So that is the field due to charge. Now, what about the field due to charge over this same region?
Charge at B.
Left or right? In the same region. Due to this B charge.
It should be away.
Away. That means right or left?
Right.
That's right. Okay. So Giovanna, just check. This EB is away from B or it's towards B?
It's towards B, so it should be left side.
It should be left side. It should be left side. This is it. Okay, now tell me. Can these two fields cancel each other?
No,
Why not?
because they are acting on same direction.
They're acting in same direction. Very good. That means neutral point cannot exist in this region. Now, Froza, let's say the neutral point lies here in region 2. What should be the direction of field over this point due to charge at A? Froza? Right, left, right, to the right hand side. And what about field due to B over the same point? Left hand side. So can they cancel each other? So neutral point can lie over. Yes, this is X. This separation will be A minus X. Yes, neutral point can lie over this one. Okay. The next is, if you want to calculate, say, consider this region 3. So Fatma, this is region number 3. So what's the direction of field due to charge at A over this region 3? Fatma.
It will be away,
Away means right or left?
the right hand side.
Right hand side. And what about due to B?
Same, right hand side.
They cancel each other?
No.
So that means field. So the only possibility for neutral point is this. Let's say this separation is X and this will be A minus X. And I call this as neutral point. So you can write this as at neutral point EA plus EB is 0. The vector sum of both the fields is 0. EA and EB is 0. Angle between them is 180 degrees. So you can simply write this as EA minus EB is 0, or you can write this as EE is equal to EB. Okay, do one thing, just substitute the values of EA and EB and get the value of X. Try to solve it on your own. Just put the values of E and EB and get the value and get X. Yes, so EA is, it's K E over X square, and EB is K4E over A minus X square. So this K will cancel K, E will cancel E. Just take roots on both the sides. So 1 by X is 2 by A minus X. So when you cross multiply them, it comes out to be, it's A minus X equal to 2X, then A is 3X, your X will be A by 3. Okay, now solve the same question. If you get this concept, then solve the same question if this charge is negative. Same question if the charge is negative. Now I don't know in which region the neutral point will lie. First of all, decide region in which neutral point can lie. If you came across two regions where you can find neutral point, then just tell me. First of all, decide regions where neutral point can lie. 1 and 3, good. So now, if you have a confusion in two regions, that if you find neutral points in two regions, then use this shortcut. Yes, so you all are finding neutral point in region 1 as well as region 3. Neutral point cannot lie simultaneously in two regions. It will either be in region 1 or in region 3. So the direct way to detect in which region neutral point will lie, if you have choices, then you can simply use this statement. Neutral point will always lie near charge having smaller magnitude. Smaller magnitude. So Fatma, you two are getting neutral point in region 1 and 3?
Yes,
Okay. So which one is smaller charge? This E is smaller?
it's positive.
Don't look at
I just
don't look at the sign of charges. This plus and minus won't decide the magnitude. Just
so plus E is smaller.
this is N1. Let's say I'm saying this is neutral point N1 and this is neutral point N2. Which one is near the smaller charge? N1 or N2?
N1. N1.
N1. So this is the neutral point of the system. So whenever you came across two regions in which your neutral point can lie, there's a simple method that neutral point will always lie near charge having smaller magnitude. So this N2 is not the neutral point, N1 is the neutral point. Let's say I call this separation as X from one charge. And from the another charge, this will be A plus X. Get the value of X now. The net field over this neutral point is due to charge at A. This is EA. And then this is due to charge at B, which is towards the charge, it's E. So net field at neutral point is 0. That means the vector sum of EA and EB should be 0. Now, since EA and EB both are acting in opposite directions, you can write this as EA minus EB is 0. Or you can simply write this EA is equal to EB. So EA is KE over X square and EB is K4E over A plus X whole square. So the K will cancel this K, E will cancel this E, and we are left with 1 by X square is 4 by A plus X square. So take roots on both the sides. So this is 1 by X is 2 by A plus X. So if you multiply them, you'll get A plus X is 2X. Then A will be equal to X. Okay, the next question is, instead of two charges, what if you have more than two charges? Let's say you have a system of 4 charges. You have a system having 4 charges. It's plus E, it's plus 2E, it's minus E, it's minus 2E. This is center O. This is the center O. This is point A. This is point B. This is point C. And this is point D. Each side is A. So you're supposed to calculate net electric field at O. Calculate net electric field net electric field at O. Now, to calculate this net field at O, you will first need this the separation AO, BO, CO, and DO. So if the side of the square is A, can you tell me what is AO? How much is AO? If side of each square is A, each side of square is A, then what is AO? It's half of diagonal. AO will be it's half of the diagonal of square. And the diagonal of square is root over A square plus A square by 2, right? So it will be A root 2 over 2. So AO comes out to be A by root 2. From now onwards, I will use this directly in numericals. The half of diagonal, which is AO, is A by root 2. This we will use directly in numericals from now onwards. Now, AO, BO, CO, and DO all are equal to A by root 2. That's it. Now, you need net field over this point. Also, all charges will generate fields at O. Due to charge at A, this should be the direction of field, that's EA. Due to charge at B, this is the direction of field, that's EB. Due to charge at C, C is a negative charge. This is the direction of field due to EC. Charge at D, this is the direction of field due to ED. Now, this EA and EC, as you can see that they should have equal magnitudes for both. Here is E, is again E, the separation is same. So EA and EC have same magnitude. So that is K E over A by root 2 whole square. So this is K E over A square by 2. So EA and EC are equal, and that is 2KE over A square. Similarly, this EB and ED, since charges are same, only the difference in their nature. So the direction of fields would be different, but magnitude would be same. So you can say that EB and ED are equal, and their magnitudes are K 2E over A by root 2 square. So EB is equal to ED, which is twice of KE over A square by 2. You can take this 2 in the numerator. So when you take this 2 in numerator, this is simply EB is ED, which is 4KE over A square. So EB and ED are equal, which are 4KE by A square. E and EC are equal, which is 2KE by A square.